Hi, I'm Mr. Miller, and this is a lesson on proving identities. So before I get into these examples, we're proving trig identities, and we're doing proofs for all permissible values of x or theta, whatever the case may be. I wanted to just take a moment to show you trig identities like this. These are the Pythagorean relationships. You can actually take these and rearrange them to suit your needs. So sometimes it's useful to have sine squared theta plus cosine squared theta is equal to 1. But you can also rearrange this equation like so, isolate for one particular term. So you can write that cosine squared theta is equal to 1 minus sine squared theta. And you can also write that sine squared theta is equal to 1 minus cosine squared theta. So although the equation is written in this way, you can actually solve it for other terms if it's helpful. So likewise with the tangent and secant, the way that they're related in this Pythagorean identity, you can take that equation and rearrange it to suit your needs. So for instance, you can take this one and say you get 1 when you do secant squared theta and take away tangent squared theta. Or you can isolate the tangent squared theta term, and that would be equal to secant squared theta minus 1. So there are a few different ways of doing that. And so finally, for this relationship here, you can rearrange it to use it in this way. You could say, all right, so I've got it solved for cosecant squared theta, but maybe I want to have it solved for cotangent squared theta. So you can write cotangent squared theta is equal to cosecant squared theta minus 1. Or the other thing that you can do is you can write it as 1 is cosecant squared theta minus cotangent squared theta. So a few different versions of the same identity. So just keep that in mind as we're doing these identities. So moving back over now to the notes on proving identities, and of course we're talking about trigonometric identities. And the task here is to prove that the following identities are true for all permissible values of x. So a few rules here around proving trig identities. So first rule is you have to split right down the middle of the page. So underneath the equal sign, you'll notice I always put a line here, and you're not allowed to move any terms from the left onto the right, and you're not allowed to do any cross multiplying. Part of the reason that it's not allowed, it's not that it's mathematically invalid, but it means that you wouldn't have to use very many of your skills in simplifying algebraic expressions to do these proofs. So there are a few things that you're not allowed to do, and yeah, one of them is moving terms from one side of the equation to the other side of the equation, either by adding or subtracting or multiplying, dividing. Okay, so what is on the left stays on the left, what's on the right stays on the right. And you'll notice that it says prove for all permissible values. And so sometimes what we do is we have follow-up questions where we say, what are all the permissible values of x and what are the restricted values? So obviously tangent is not defined everywhere. So it doesn't make sense to talk about this identity anywhere where tangent is not defined or anywhere where secant is not defined either. So that's just some other things to keep in mind. So let's focus on the actual proving part now. And what I notice with this proof to be done is that we've got, on the left-hand side, we've got this tangent x minus 1, which all of it is squared. And one of the things that I can do is I can do some expansion, right? I can do tangent x minus 1 times tangent x minus 1. And here's what I would get as a result. Once I do that, I start to recognize, okay, I notice that there's a -2 tangent theta, -2 tangent x on the left, which matches the -2 tangent x on the right. And so what I'm going to do is I'm just going to rearrange this a little bit to put that on the end. And so now I look at what's remaining here. I've got tangent squared x plus 1, and I've got secant squared x on the other side. And well, tangent squared x plus 1 is equal to secant squared x. So I can just do that substitution using that Pythagorean identity. And so again, I can go back to the notes that I was writing up here. So I notice that tangent squared theta plus 1 is equal to secant squared theta. So that means that I can do this substitution here, and now I have a match for what I have on the right-hand side. So once you have a match, left-hand side and right-hand side, then that's all you need to do. You notice that I didn't do any manipulation of what was on the right-hand side. And so sometimes students ask, should I work with everything on the left or should I work with everything on the right? And there's no saying that you have to work with things on the left first or that you should always work with things on the right. You can work with expressions on either side. Often what we do is we try to take the more complicated side and simplify it. Or sometimes if we just know some algebraic steps that we can take on one side, then we go ahead and do that, which is what I did in this case. So here's another example of a proof to be done. And so I've got these two things that are apparently equal to each other. This is an identity. We want to prove that it's true for all x. For all x where this is defined. Obviously, anywhere that makes cosine equal to 0 is not going to be okay. And anywhere that sine is equal to 1 is going to make that denominator 0. So there are some restricted values, which we can list, but we'll focus at the moment just on the proof itself. So here is another thing that you can do to manipulate one side of the equation. So now this was a little bit arbitrary. I chose to do a manipulation of the right-hand side of the equation. I could have done the left. Both sides are about the same in terms of how complex they are. But if I multiply by a conjugate, and so I'm doing the conjugate of this numerator, instead of 1 plus sine x, I've got 1 minus sine x. Now multiply the top and the bottom by that. What you'll find is it leads to a difference of squares on the top, and that often leads to a Pythagorean identity that can be used. So just going back to the Pythagorean situation, I've got 1 minus sine squared theta is equal to cosine squared theta. So my 1 minus sine squared x can be replaced with cosine squared x. And at this point, you recognize that there's a common factor of cosine x that can be divided out between the top and the bottom of this expression. And so I'm left with cosine x over 1 minus sine x. And at this point, I have a match for the expression on the left side of the equation. So this is one way to do this proof. Here's the next one. And so if we take a look at both sides of the equation, we'll notice that the left side is definitely more complicated. And so one of the strategies that you can use is you can replace anything that isn't in terms of sines and cosines and replace it with sines and cosines. So I'm using that quotient identity for tangent. And in the bottom, I've actually used the Pythagorean substitution here, 1 plus tangent squared x is equal to secant squared x, because that's definitely simpler to have one term here instead of two. And now at this point, on the other side, I also recognize that sine 2x, well, I do have a double angle identity that I can use, which is 2 sine x cosine x. And just some more manipulation I can do. I can replace the secant squared x with 1 over cosine squared x, because my goal is really to change this side so it's all in terms of sines and cosines. And you can see certainly that's all I've got on the right-hand side is just sines and cosines. So I've already replaced the tangent with sine over cosine. The tangent squared x, when I add 1, I get secant squared x. That's good. That's a single term instead of 2. But now if I replace that secant x with 1 over cosine, and I'm squaring that, now I've got an expression, the entire expression on the left-hand side of the equation that's only involving sines and cosines. And so now I can just take this, I'm going to flip and multiply, and I'm going to simplify, dividing out a common factor of cosine x, and we're left with just 2 sine x cosine x, which is a match for what we have on the right side of the equation. And here's the final example here. So obviously the left side of the equation is quite complicated, and so I'm going to attempt to do some simplifications on that first, and then if we need to, we can do some manipulation of the right. So starting with the left, I am going to use a common denominator between these two denominators, and the common denominator is the product of those two. So you notice that I'm multiplying this denominator by cosine x in order to get an equivalent fraction here with a denominator of 1 minus sine x times cosine x. I have to multiply the top and the bottom by cosine x. The other term, I'm going to multiply the top and bottom by 1 minus sine x, and here's what I get. So cosine squared x plus 1 minus sine squared x. And the denominator is 1 minus sine x times cosine x. Excuse me. All right, so at this point, I can do some simplification. So I notice that the 1 minus sine squared x is there. I can replace that with cosine squared x. Now I have two like terms in the numerator. I can add those two together. And finally, I recognize there's a common factor of cosine x with the numerator and denominator that can divide out. And so here's what I'm left with, which is a match for what I have on the right side of the equation. So I'm just going to read through the summary at this point. To prove trigonometric identities for all permissible values of a variable means we're doing an algebraic proof. So if you're initially wondering about a trigonometric identity and whether it's true, you can substitute a single angle to see if it makes the left side of the equation equal to the right-hand side of the equation. And you can certainly graph both sides of the equation to see if they match each other, but a really complete proof that proves it for all x is an algebraic proof. So although there are many different types of algebraic proofs, from very simple to complex, there's no simple sequence of steps that you can go through that guarantees a proof for all possible identities. So instead, we've got a bunch of strategies that have been illustrated here in our examples, and I'm listing these possible strategies that we could take, and each strategy should be used where it's appropriate. So here are some of the strategies that we have seen so far in these examples. So use some known identities to make substitutions. That's one thing that you can do. If you have quadratics present, often you can use Pythagorean identities to do further substitutions and sometimes simplifications. You can rewrite expressions using only sine and cosine functions. You can multiply the numerator and denominator of an expression by the conjugate of something. So if you have a 1 plus sine x, you can multiply numerator and denominator by 1 minus sine x. This leads to a difference of squares and a Pythagorean identity that can be used to simplify in some cases. Factoring to simplify an expression is a good thing that you can do. So as you can see, there are a number of things that you can do to make progress in doing a proof. So thanks for watching this video on proving trigonometric identities, and have a great day. Bye.